I guess we are almost online. Okay, now we are online. Hello, good morning, good evening. Welcome to today's talk in our module Emerging Fields in Architecture from TU Vienna. Today we have a special guest from the US. It's Sam Ximenes. Sorry,
That's good.
help me. Ximenes. Sorry. Today we have a special guest, Sam Ximenes. He's a space architect, has over 30 years experience in the aerospace industry. He has worked with NASA and worked on a lot of international space programs. I do know Sam for quite a while. We haven't met in person, as you can probably see from my introduction, but we have worked together with the Space Architecture Technical Committee, and he is a very long-term member of this committee. And also in 2023, he was inducted into the San Antonio Aviation and Aerospace Hall of Fame. He has a company that is called Exploration Architecture Corporation, XR. It's a space architecture consulting firm that he founded in 2007. I am very pleased that today we see two projects from him, and his company, the Exploration Architecture Corporation, specializes in commercial spaceport development and design, and also space systems development. And it is for space exploration projects, for planetary surface systems, for habitation and human settlement. And Sam Ximenes is also the founder and board chair of WEX Foundation, which is a non-profit organization for advancing careers in space exploration. So he has also been very busy and very interested in space STEM education. His latest venture is that he is the CEO of Astroport Space Technology, which he founded in 2020. And I'm looking very much forward to hearing more about your project. Thank you for sharing your work with our students. Welcome, Sam.
Thank you very much. Excuse me if my voice is crackling a little bit. I'm just getting through with a little bit of a cold, but I'm glad to be here. And I also am very enthusiastic about sharing some of our projects from the architecture side, which is the Exploration Architecture Corporation, or XARC, and then also from the civil engineering side, which is Astroport, which is doing the actual construction technologies necessary for doing the building of building lunar bases and habitats and lunar outposts. So I think I'll start with, I have two presentations. One is, like, as I mentioned, I'll go into I'll start with the civil engineering piece of it. How do you actually begin with the actual construction of laying down foundations and infrastructure? Let me see if I'll get this share screen going and start with that one. And then give some presentation mode. So can you see the screen?
I can see the screen of your, now it's the presentation mode. Great.
Okay. All right, so this is pretty fanciful. This first image here. What we're trying to do here is show that potentially we could go to a lava tube pit and build out the surface system, portions of it on the top, and then eventually get down underneath into the lava tube cave, and in the long term, end of the century type of thing. You know, many years and decades down the road, possibly cover it with a dome, so that we can get out of the pressure suits and the habitats and have a little bit more freedom to move around. So that's kind of a vision of the end goal here. Here's kind of what we were looking at in terms of again, this is just a concept of what something could potentially look like in the far future, once we have all the technologies and the ability to move material and efforts of technologies that for building understood and built out. When we talk about living in underground lava tubes, either on the moon or on Mars, there's going to be just as much surface system architecture as there is going to be underneath it. And when we try to live underground in a pressurized environment, potentially. So you can see here there's a spaceport in the background there. There's a nuclear reactor up in the on the left-hand side. And then there's a mining operation going on in the forefront. Then underneath it, there's a habitats and some sort of industrial complex going on where they're doing the business of the economy, the lunar economy, what we call the cislunar economy. It's the economy that's going to be developing very much in the next decade, even beginning in this decade, where we start seeing commerce being developed for the lunar surface, especially in the beginning when we start talking about building out the infrastructure and mining the moon for oxygen and fuel consumption. So that's kind of where we want to get to. That's how do you start? What's the beginning stages of that? You want to do a basic layout of a site. There's some pretty basic things that go into any kind of development of a lunar site. You need power, and you need lots of power. Power is king to do anything on the lunar surface, and so you want to bring as much power as you can. You begin with solar power, and then put in a nuclear reactor and that's actually being done right now. There's a goal here in the U.S. to put a 100 kilowatt reactor on the lunar surface by 2030. But before you can even do that, you need a landing pad. You need to be able to land so you can bring material, you can bring resupply as well. Then you have your operations that you're doing, whether you're doing surface mining or you're doing fuel development, where you have storage facilities, and then there you see kind of the beginnings of the developing that lunar pit into some sort of a structure that will be able to accommodate a habitable zone of some sort. So what's the problem we're trying to do before you even begin? I got mentioned earlier, you need landings. You need to be able to land safely. And this is kind of the first problem that needs to be solved, is to be able to land on the surface, because of, it's a pretty uneven terrain. It's dangerous. You have dust plumes that generate when you start landing with big rockets like the Starship, where it's pretty energetic. The dust that is blown out when you start landing goes into high energy trajectories, possibly even into orbit around the moon. So you need to be able to have a prepared surface to prevent this, the dust from being disturbed and getting all over the place. Today, there's only been a 38% success rate over the last 12 years of landings that have tried to get there. Some have gotten there but fallen over and tipped over or landed upside down. Some have crashed. So the landing pad is very important. This is what Astroport does. This is the subsidiary corporation that's doing the civil engineering that I mentioned earlier. So our goal here is to develop landing pads on the lunar surface, and we do that by taking the dirt. I've got a movie here. It's kind of long, so I won't play that. I'll play some other ones later on. If we have time, I'll come back to this one. So you need the landing pads to do many things. For, again, safe landing. You need roads for the surface mobility, haul roads, and dust-free zones for all the activity that's going to be occurring there. Why the landing port? It's actually the gateway. It's a gateway to this lunar community and the beginning of the commerce that you're going to need to that will be developed there in terms of the activities of the base. Just like any spaceport here on Earth, we've been developing spaceports from Spaceport America to Spaceport Houston, and what we find is that they're economic engines. They drive the economy of the community. There's businesses that surround the spaceport or even come on the campus of the spaceport for manufacturing and high-tech businesses. And it'll be the same thing on the moon as well when we get to the point where we can actually have a reliable transportation system be able to come back and go back and forth and developing the commerce. So this really is the catalyst for the spaceport is the gateway. And you get there in stages. You have the beginning stage in the first 10 years. There's going to be pretty much basic dirt pads or some kind of improved hardened surface with basic, berm protection for the blast shields. And then it's pretty rudimentary. But then you get to the next stage, which is the depot stage, where you start servicing the assets that are being delivered, like the robots and the mining equipment. You need to be able to, it's all going to break down at some point. It's going to have to be refurbished. You're going to be doing recycling. Anything you bring to the moon is valuable. Even the packaging material that you use to package whatever you have packaged into the fairings of the rockets. That's just as valuable as anything else. So you need what's called the MRO facility, a maintenance, repair, and overhaul, sort of a depot where you're taking the maybe landers that have 2 stages, a descent stage that stays behind. You would keep that, pull it out off the pad and tear it down and turn those metals into building materials. So that's the next stage that we would go into. Then eventually, as you see at the end, again, the vision to get the full blown settlement, maybe 100 people living there in the end of the century. So here's the construction part of it. So we're doing the Astroport is doing construction, taking the moon dirt and turning the dirt into bricks. We melt the dirt and we use it as the building material. Essentially, the hardened solidification of the lunar dirt is the first thing we would do with it. It's got a lot of applications to it. You not just can melt it, but you can also extract metals and minerals out of it and gases as well. So you have to deal with space materials. There's a lot of research and engineering and science, material science that goes into understanding the regolith. It's going to be very important down to the granular level, understanding how it behaves, the characteristics of it, the physics of it. And then we get into don't just make bricks. Then you got to figure out how to place the bricks as well. Excuse me. That's the robotics that come into play. So you have to develop the robotic machinery, the autonomous robotics. We're doing this autonomously with minimal intervention by humans that are there mostly for inspection, intervention, and maintenance. So that construction piece of it is the next. Is what happens currently, right? What we're developing. But then we get to the landing port when we start becoming operational. That's the game for us, is to be able to service the landing port, be a service provider, taking the offloading of the material, offloading of the cargo, forward movement of the cargo as well. So that's kind of what we want to get to in the end of it. Excuse me, I'll get some water here. So as I mentioned, the lunar soil is pretty much very versatile. You have minerals in it and volatiles that can be extracted out of it. You've got the aluminum, iron, magnesium, titanium. There's gases in it that can be extracted. Gases like oxygen and helium-3 that are trapped into the grains. And then, of course, water is actually in there as well. So these all can be extracted, and these are all useful for an economy, for a business, for building materials. And again, you can turn it into actual building materials such as bricks and rebars and fibers and geotextiles and even glasses as well. Glasses for solar panels, for example. So what we're doing at Astroport is we're taking the bricks here. This is some of the state of the art right now that we're at in terms of building these bricks. These are full-size bricks, 160 millimeter by 50 meter height. These are typical paver size that you see in any kind of road or a pathway. Yes, they're very high strength concrete. Then there's also the ability to take that and manipulate it into different forms and shapes as well. The big challenge for this is to try and do this in a vacuum. The same sort of densities we can get in ambient air is very difficult to get in a vacuum environment, and we're learning how to do that as well. We have some technology we're developing for 3D printing, where we take the actual regolith, combine it with the PLA, turn it into a filament, and then we can 3D print it, layer deposition printing, for example. You see in the top there, top right, there's a large hang printer that we've been developing that can print from meter to meters in size and then height as well, depending on the layout of the truss system that you see there in the picture. Then we've been developing how to take fibers out of the regolith, fibers for glass crystallization, fibers for optical electronics, and turning the as I mentioned earlier, the regolith into a glass for solar panels as well. So these are one of my point here is that if you're gonna build on the moon, what are you gonna build with? What are your materials? You can't bring that all with you. It's too heavy to bring, too much payload and mass to be delivered to the surface. There'll be some of it being brought, but in the most part, you want to take what's there and build from what is already on the environment you're living in. Now we go to the construction part of it. So we're developing the robots the construction robots for the excavation and the site level and site preparation that needs to be done. Just like any civil engineering project here on Earth, you'd have to survey the site. There's a surveyor robot we developed to go and do the ground testing and the soil mechanics or just understand what the soil densities are and the strength of the soils that you're going to be building on. And then again, once we get there, then we get there with excavation tools such as excavators and shovels and compactors. Let's bring a short movie here for the compactor we've been developing for our technology demonstrator. Let's see if this will work. Looks like we got a stall here. Sorry about that. Let's see if we can get out of it now. Are you still there?
Yes.
Yes.
Looks like the video stalled. The video stalled on me, so let me get out of it. All right. Sorry about that. Let's try this other one. This might be a little bit easier. This is the compactor we just got through developing. This is a subscale version of it. That's 1/13 scale, the size we would actually be building. We just demonstrated this in Australia.
They've got pressure cells in there, and we can actively track the actual compaction that's going on the surface, under the surface rather. It's also good to have this type of scale model. Means we can put it in our vacuum chamber and also investigate the effects that vacuum has on compaction. So obviously on the moon we don't have air in the soil. How does that affect things when we're trying to compact?
So as you see there, that he mentioned about vacuum. It's really important that we understand how all these tools and materials work in vacuum. We can apply them here on Earth with an ambient air, just to understand the core principles. But then as you mentioned, we need prototypes and scale models to put them into the vacuum chambers, and so that we can understand the different principles that apply to the vacuum environment. We've been doing work with NASA. Our work is funded by NASA for the most part. We've been getting funded from NASA for the last 4 years, developing the concept of operations for what does it take to develop the landing site itself, specific to the landing site. And as I mentioned, all that includes the development of the robots, the regolith conveyance. How do you, once you excavate the regolith, we're talking about moving metric tons of regolith, tens of thousands of metric tons of regolith needs to be moved around, especially if we're going to the South Pole. It's very hard to find a flat surface, and we have to do cut and fill operations. And then what do we do with all that regolith and for making the bricks, for example? we have to convey it. So we're doing conveyance technologies. We're developing silos, systems for sorting and sieving the regolith. Working with the University of Wrocław in Poland. It's one of our partners in this project. We're an international team. We have a University of Adelaide in Australia as part of our team. A couple of companies in Luxembourg as well. We have a Luxembourg operation that has been there for like 2 years, getting started for developing some of these technologies through the ESA as well. So all this has been developed down to how do you actually land there with the assets, the equipment, the packaging into the rocket, and then how do you begin the first phases of the staging and the setup as well. This is just a little bit of a construction sequence where you land, you unload your equipment, you got to set up first of all before you can begin construction. Set up your power system and your communication system. How are you going to communicate with the robots and communicate back to Earth? And then, of course, the powers are all important to get started. You need a shelter for the equipment as well, especially when the rocket takes back off. Because you don't have the protection in the beginning. That those dust plumes will destroy all your already in place assets. So you want to be able to put unpressurized shelters. Then you got to start laying cable, okay, from where your power systems are laid out to where your charging station is going to be, so that you can continue to charge your robots as they go into the process of excavation operations, where they're excavating. Now they start beginning the excavation of the site. And those, as I mentioned earlier, when you start excavating, you're digging up the soil, then you're taking it to a spoils pit or a sieving station, the silo where it's doing the sorting. In this particular case, because we're making bricks, we need to be able to have a feedstock, right, from this excavated soil that's been used for the site leveling. And that silo there, which is what the University of Wrocław is developing for us, is sorting into the grain sizes that we need to have for delivering it to the robots that are doing the brick making melters. So we have this concept of, again, it's called conveyance, where we deliver the sorted processed soil in canisters to the robots that are laying down the bricks for developing the landing pad. Site selection is important. Okay, so we talk about sites. Where are you going to land and where are you going to build is very important. We're talking about in this particular case the lunar south pole at the Shackleton crater. Over here you see on the left side the crater. The North Pole is right about here where my right here actually where the crosshairs are on this picture in the middle. And then we've located the actual site that we're developing for. So this is a benchmark site. It's a site at the Gerlache Ridge on the South Pole. And it's not to say this is the one that's going to be chosen for by any of the agencies or any of the commercial operations. But it's a site that we chose as a benchmark so we can start understanding what do you have to deal with in terms of topology and movement of soil in a realistic way. So and how do you use topology to your advantage so that you can use the elevations, the different elevations for where you locate the habitation zone versus the construction site or the landing pad. You want to have the habitation zone at a higher elevation than the landing site. Because again, the more protection for the dust plumes that would be generated, even after you have a prepared surface as well. So we started looking at the site on the Gerlache Ridge, and we started seeing some sort of indication of the amount of site level that's going to be required. This was the flattest site we could find, the flattest location that we could find at this particular site, and you can see here how it is that trying to get it flat and level. You're going to do a lot of digging and a lot of site leveling. You also have to deal with site planning. Okay, where you put your power system, for example, or even your nuclear reactor, will actually drive the way you lay out and site plan the site, so that because you have certain requirements for radiation protection. For example, you need to have 1 kilometer distance between the habitation zone and where the nuclear reactor is going to be, whether it's buried or not, and that will then determine where you put where you put your habitation and your landing pads and all your mining operations. So site planning is very important. Here we've started looking at the location of the landing pads. You can see here just movements of very few meters apart will give you different variations and different quantities of what you have to do in terms of the energy requirements for doing the site leveling. Here's what we do: a cut and fill operation. You can see the differences between A, B, and C, and they're not that far apart from each other. 500 meters or so in distances. So those are important considerations when you start doing this site planning and master planning of the location you're going to be at as well. Here's an indication of the size of the amount of dirt that's going to be moved around. You see the little arrow up here on top, this little red arrow, this little dot below it. That's a 95th percentile human male compared to the dirt pile here of 26,000 cubic meters up to 34,000 cubic meters of dirt over here. So it's a huge operation when we start talking about site level and preparation, especially at the South Pole area. There's going to be multiple robots, multiple excavators, and all that logistics and all that fleet of coordination and autonomy that needs to be developed is going to be a big task to be able to do that undertaking. Here's just in terms of the configuration of the pad itself. The design, you got to decide specific to each site whether you want to develop your blast berms. The blast berms serve a couple of purposes. They're a blast berm, just as the name implies, in case there's a mishap, an accident, where there's an explosion of some sort. You need to have a protective berm to keep it from the debris from going and destroying other aspects of the base. But it's also for protection of that blast berm, that plume blast that you're going to have. Even as we have a prepared surface, there's still be settlement of dust on the surface as well. The moon is constantly being bombarded by micrometeorites, so there's always going to be dust that's going to need to be cleared away. So that berm is important for surrounding the pad itself. Now, here's two options for the pad. Again, the configuration of the berm itself is in how do you want to develop that geometry for the ability to have dual egress. You don't want to just have one entrance into the pad area. You want to have the ability to have another exit in case of emergencies. But in this case, we chose this what we call this I-berm concept with this here in the middle. And then after choosing that, then you decide, are you going to go flat or are you going to dig down to create that berm? And you have different considerations for trying to minimize the energy requirements. You want to minimize how much energy you need to use for doing excavation, because the energy is going to be limited. So and here's a configuration for digging down. This one, by digging down, you create a natural berm. If you were to build a berm up by excavating and building up piling up dirt, then that's another aspect to, again, those trade-offs, that trade that you need to develop between energy requirements for that operation versus a digging down, where you actually create the berm by going down to a 3 to 4 meter depth, and that helps minimize, again, the energy. And it also does another thing. It provides you that feedstock we need to have for the bricks that we need to have in our case, where we're using bricks for the pavement. There's again the basic civil engineer in terms of understanding bearing capacity for the foundation itself. You have to deal with shear strength, the bearing capacity, slope stability, basic engineering, compressibility of the regolith itself. These are things that we don't know right now. That's why the surveyor bot mission is very important. Before we even go there with all this equipment, we're going to need to send a surveying robot, just like like you do on a construction site. You send the surveyors out there and do the civil engineering surveying of the site to understand what you're building on, what you're building with. So and to understand this particular site, or any site, you'll need to do that. Again, the communications, what's your communications architecture? How are you going to communicate? How the robot's going to communicate between each other if they're going to be autonomous? Are they going to work in a swarm operation? Are they going to work? How are they going to know where they are in place and time? There's no GPS on the moon. There probably will be at some point, maybe by the time we get there. Maybe those are things that are being built in tandem, but we won't rely on that. We got to rely on the robots to know their own place and location in space on the surface at any time in relation to other robots and in relation to where they think what they're doing, their key functions. So those are the communications that are a very important aspect of any architecture. One of the things that's important is as I mentioned much earlier, was the nuclear reactor. How do we deal with that reactor so that it can be placed on the at its location? At Astroport, we're developing the concept for the layout. I thought I had a movie here. I guess I missed it. I'll find it later. So we have this concept of operations for how you actually deliver the reactor, the 100 kilowatt reactor that's proposed by delivering it with in a mission on a Starship mission. Then you need to deliver it 100 kilometer distance away. Down here on the right corner, you see the landing site versus the power plant site. That's about a kilometer distance in distance. That you have to develop a haul road to get there, and this what this is doing here is this conveyor, this convey system here is a convoy, excuse me, is a grader and a compactor that's kind of making the road as it goes along. And it's got the hauler behind it that's hauling the reactor. Then you're going to decide whether you're going to dig, if you can have the topology to that can protect from the radiation without having to dig down in a big vault. You would do that, but if you don't, then you got to dig it, bury it in some manner, and then and prepare the surface. So we're preparing the surface. This is another surface preparation task, and then you deliver the reactor, and I'm going to try and find a movie here. Might be a little easier. Give me 1 second here. I thought I had the movie in the presentation, but I don't. Where's this at? So, just bear with me.
No problem, Sam.
Let's see if that works. So that's just kind of a notional concept of how we would, concept of operations, how you would actually build that base. Let me get back to where I was at. Again, you saw where we're trying to build that haul road to deliver the reactor to the site location. And then after we just deployed it, then we build more burns to do the radiation protection requirements that are needed. This is another movie. I think it's just a time. I won't do this one. This is a little bit long as well. This was a movie, and these are on YouTube. That's on our YouTube site. You can go to our site and you'll see these that are the concept of operations, how the pad gets built out. We also developing the simulation models that develop I'll keep talking about energy requirements. Energy is very important in terms of because you only have limited power, and the energy required that you need to use for those robots are very important. How they coordinate themselves, and you want to minimize that. So we're doing simulations of the traverses of the robots, how far they have to move in any given task that they have to do, and coordinate and understand that to understand what are the power requirements that we're going to need to have as well. And also simulating when something breaks down, when you need a spare, because you're going to be running out of the regolith is very caustic and very dangerous and very abrasive. It's going to tear down equipment very fast. And you need to deal with spares and change out of equipment, change out of the shovels, change out of the excavators. So those are things we have to simulate to understand how much we got to bring with us to continue the operation in terms of spare parts. Again, you got to deal with cargo offloading. How do you package all the equipment? How do you put it in where now we have this concept of cargo containers. How do you package it so you know that you have enough equipment that's going to be necessary to do the first operations. You're going to have to do it more than one landing, more than one mission. These are things they all get driven by. It's a chain reaction. One thing changes in your concept of operations, and it basically changes back all the way back to the beginning of even the rocket launch and what it brings with it. So understanding packaging of the equipment is important. And then how do you manifest it once it's unloaded? Again, these are all models we're developing, physical models, as well as digital twins we're developing, a digital twin environment to help us understand, the simulations that we're developing, and we're trying to employ AI for that as well. Test. So before we do all this as well, before we even get up there, we got to do a lot of testing here on the ground, and we're developing all these processes in a lunar yard, which we're going to develop a place called Midland, Texas, Air and Spaceport there. We're trying to build a one-to-one simulation analog of the site itself to the extent that we can. This is a full scale, but the distances that are in our site plan are condensed here. This is for example, the two landing pads are pretty close together, which wouldn't be the case. They need to be at least a kilometer apart because of the limitation of trying to build a one-to-one scale. We're doing this where we're actually full scale, but at limited distances, where we're going to be testing the landing pad construction. Back here in the corner, we're going to be testing the deployment of the reactor itself. These are all for understanding, again, the processes, the traverses of the robots, and how far they have to go and how much energy they need to use. Just trying to understand that in this environment. And then we also have in 2 phases. We'll be building this large dome structure here, which will be an interior facility for more controlled environment of the regolith. So we can have on the outside is more of a granular level that's more conducive to the outdoors. So again, the test facility is going to be very important. The ground test facility is going to be just as important as before you even get to the lunar surface as well. So we've got some pretty good traction in the media here. We were just recently featured in the National Geographic, the September issue, talking about what we're trying to do on the lunar surface, that we're part of this lunar economy that's trying to be developed, and that we're trying to make a business out of going to the lunar surface. I think that's that one. That's it for that. I can take a break here before I go into the next presentation, which is which is the lava tube part of it. If you want to do that, or we'll go straight into it as well. Or if we are out of time, I don't know if we have more time or not. That's kind of more than I thought I took.
Thanks a lot. We have already some questions. Probably it would be good to answer a few questions now.
Okay. Let me see if I don't know if I can get to the
Luca,
question.
I think you were the first one. Best is you turn your camera
Yes.
on, or
Yeah.
at least micro on, and ask the question yourself, please.
Sure. Just let me get the question on my screen so I don't repeat it wrong. So a question in general, how will the project construction and robotics deal with the electromagnetically charged dust particles? So because it could interfere with the robotics, engineering, and so on.
Yeah, it's a very good question. As a matter of fact, we've been initiating the internal project at Astroport, start dealing with the electromagnetic dust issue we're going to have. There's all kinds of investigations going on right now with NASA, everything from magnetics to material coatings to prevent dust from accumulating, or maybe have a coating that would not let it adhere to build electrostatic charge. But these are technologies that are being developed at the moment, and we are dealing with that. We're trying to deal with that in terms of understanding the technology solution for that for the electrostatic buildup.
Right. Thank you.
Thank you, Luca. Thank you, Sam. Mark and Leon, please.
Can you hear me?
Yes.
Yeah. Hi. We just had a question about the nuclear power plant, which tries to be constructed on the moon side, and isn't it a big problem by a landing rate of 38% and dealing with nuclear things which will contaminate the moon for ages afterwards if something happens? Isn't it the chance to think of renewable energy sources? I mean, the problem is of course the transport and the energy density, which is very high in nuclear power plants, but for me, as an amateur, it doesn't seem like a good idea.
So nuclear power has been used in space for many, many years, since the beginning of the space era. And there's a new technology, there's a new generation of reactors that are being developed right now that are not as dangerous, or not even to the extent that we think about when we think about nuclear reactors, like the Chernobyl type of reactor. The one thing that you bring up that would be a problem is the landing part of it, with the initial landing, because the initial landing won't be a prepared surface; it will be unprepared, and there are concerns about landing a bit large starship with the tall the center of gravity that could maybe topple over. That would be more of a damaging the whole mission. There would not be a reactor spill or a contamination spill with these kind of reactors. They're inert before they're turned on. So there wouldn't be that kind of an issue at all. The more problematic issue would be a failed landing that would with this 38% rate. So those are more of a concern than the radiation part of it. That would be not there in the case of a crash as well, because it is an inert at that point.
Thank you.
Thanks a lot. Stefan, you had a
Yes.
question?
Hello. I just wanted to know, would you say there are benefits or disadvantages on construction sites on the moon compared to Earth with the gravitation as main difference?
You want to know the differences between Earth construction and lunar construction?
Yes, kind of,
With
because of the
gravitation?
gravitation differences.
Yeah. So, well, of course, the gravity is the big issue. 1/6 gravity, and how do we test for that on Earth? And again, part of that lunar test site we want to develop, they'll have techniques for gravity offloading, where we would try to simulate the 1/6 gravity by different techniques, different mechanical systems, but we can't get it exactly all the time. And one of the things you have to deal with one big issue in construction excavation is that we don't have the weight here that on the moon that we do here on Earth. When we talk about bulldozers and heavy tractors, that they all rely on reactive forces, right, and the weight of the vehicle itself. And because we don't have that weight on the moon with these equipment, we have to excavate in a different kind of way. The excavator I was showing you, which has been developed by NASA, and we have a license from them to develop for our own purposes. But the basic concept of that excavator is that it doesn't dig; it scrapes. It scrapes the little bit by little bit in terms of the way it digs up, and that helps with the ability to not have that weight that you would have if you had a big bulldozer or a big tractor on the ground. So,
Thank you very much.
so you do have to develop your machinery in a different kind of way.
Thank you very much.
Thank you both. So we have a question by Ayem and then by Tobias, please. And then we can start with the second part of the talk, if you don't mind, Sam.
Okay.
Hello, can you hear me?
Yes.
Thank you for the interesting lecture. It was a great input. I was wondering, would smaller scale robotic systems, so-called swarm robotic systems, reduce redundancy in situ construction and extraterrestrial environments? What do you think?
I don't know about reducing redundancy. Of course, they would be, and we're looking at the way. Is it a swarm or is it really just more a coordination of multiple robots? The swarm is a little bit different kind of an application because it's all doing in a sort of a tandem path or a coordinated path, as opposed to robots that are going in different directions for different operations. So I don't know about the redundancy trade that would occur. The swarm is not really it's not really that conducive to the construction because again, you have robots that are doing different operations. But one thing that happens is that in terms of the redundancy, we have I showed you the platform, the robotic platform that is that had different tools on it. So we could bring up one of the a multiple of that's kind of what we're doing right now, simulating how many robots we need to have. But once we understand that, we want to minimize that, and then each, instead of having one robot for one function, for example, one robot for a excavator or one robot for a compactor, that same robot platform could be interchangeable. It would swap out the compactor and put a grader on it as well, or put the brick maker on it. So you have then the interchangeable tools that go onto the one platform, the robotic platform, and that helps a little bit with again some of the redundancy. But trying to determine how many platforms you need to have is what's the challenge right now we're trying to solve with our simulations. Bottom line on the swarm question, I don't think swarm would be the right way for the construction part of it because of the different operations that are occurring at the same time. I don't know if that answered your question or not, but
Thank you. It was very insightful, very interesting. Thank you.
Sure.
Hello. I was wondering about the bricks you showed, the regolith bricks, and why you chose bricks instead of laser sintering the regolith in place for the paving of the roads and the landing pads.
Yeah, there are a number of operations, ways you could do that. Laser sintering, you could do a concrete, laying. We went to the easiest way we thought we could do this. I could call it low hanging fruit, where we could just melt the regolith directly and make the bricks one at a time. We have a way of doing those bricks so that they can be laid down and melted together. Essentially, it's a fusion process with a patented nozzle we developed that allows us to put the one brick down at a time, and then the next brick that's placed next to it is fused together. So that alleviates the need for grouts and mortars for the pavers as well. So in that way we can make a thicker brick. Laser sintering, when we started this, the technology was not that quite developed. So you can have the thickness, the laser, going down into the soil to get a nice thick without it cracking or breaking. And we didn't know what the densities were at that point in time. So I think it's gotten better now. There's some companies that claim they can go down to a meter of depth, but I don't, I haven't seen any proof of that yet. Just claims. So I don't know where the state of the art of this laser sintering is in terms of the durability of the sintered pavement to withstand the loads of the rack of 100-ton lander coming down with cargo lander as well. It might be useful for other things, for laying down a quick path, walk path, or maybe a road, or some dust mitigation. So each technology, each construction method will have its different purpose, different application. Just like on Earth, we have different ways of making things with the same structure. It'd be the same thing on the moon with different applications, different technologies, all doing its particular function as well. They're all valid in some regard.
Thank you.
Thank you, Sam.
Okay.
You would have to share your screen again, please.
Okay.
I have to thank you in the middle for your comprehensive information. Lots of information compactly communicated. Very interesting.
Well,
Thanks for
thank you.
sharing.
Yeah, sure. I might speak a little fast, so you might want to use a video YouTube to go back and try to grab some of this up.
I guess it would help if the students are interested and they want to use the information for the project. I think that's one advantage of having it recorded, because you really put a lot of information on a few slides, which is fantastic.
Okay, so now that we've got a surface operation, we have a landing pad, developed in their surface operations, and we can get there with a good cadence of delivery of material and cargo. We want to start figuring out how do we get down into the landing, into the lava tube itself. Now, I talked to you earlier in the first presentation about a South Pole location. We have not found any lava tubes in the South Pole yet. Mostly they're on the Mare region, but the same principles apply to the landing and construction operations as well. And this particular location that we're looking at is a location at Maria's Hills, the equatorial region of the moon. I'm not going to go through this. Is kind of a background on XARC. I won't do too much of it here, but we do, again, planetary surface systems. We do an orbital architecture, learning about space stations. We've been developing that for some time. And then again, I mentioned the spaceports that we develop here terrestrially. So we're interplanetary architects, basically. We talked about that. Here's the lava tubes. So there's lava tubes that are found on all the planets, Mars and the Moon pretty much anywhere there's a geologic or volcanic activity. On Earth, the largest lava tube we have is this one in Vietnam, Hong Song Doon Cave in Vietnam. You can see a kind of a scale, sense of scale here, 48-meter, height of this cave. Down at the bottom, you see there's a person down here, a couple of people down here, so it gives you the sense of scale. This scale is what we think is what we will find on the lunar surface. As the typical size of a lava tube. They're very large. The Marius Hills volcanic complexes we're looking at the crater area. Over here in the corner, you can see where the Marius Hills tube is. You can see here, there's a little kind of a animation of what they discovered. This was discovered back in 2007, I think, somewhere in that time frame. That was the first one discovered by the Cayuga satellite, the Japanese Selene satellite. I think it's called Cayuga Selene. But this, you can see here the visual of it as it comes in. And on the right side here are some still images of the pit itself. So I think that's yeah, that should be enough. Okay, I talked about this one here, where the objective is to develop it for lunar operations. And we can cover it with the dome at some point in time. Sorry, this is kind of an older presentation. We talked about this already, what we're trying to do at this particular site. We talked about this already, kind of the end goal, the end game. We want to get down in there. This is a little bit fanciful, but what if we could do something like this, where we can actually live in a pressurized environment on the lunar surface, with instead of living in tubes and habitats that are cans basically, and we can get out of the spacesuits and live in an atmosphere that just gives us more room to move around at and live in more livability, habitability. I think that we will have arrived, if I can use that term, as a settlement, once we are able to bring our animals with us. You see here a cat in the background here. That's I'm just throwing that out there. I think that would be an indication that we've been able to solve the problem of living on a different planet if we're able to bring our pets as well. I don't know what's going to happen with animals when we go into the solar system. It's a big question I have. Just the images of what could be potentially. So that what they're doing there is they've got a business. It's an industry. They're developing an economy. Maybe they're doing helium-3 mining, or they're doing fuel production, and they're exporting it to orbiting depots or fuel depots that are going on to Mars or whatever. And of course, greenhouses, developing oxygen for being able to. All the gas that's going to be required to do something like this is horrendous. It's a huge amount of gas. Again, these are practicalities that need to be thought about when you start looking at pictures like this. Well, how much gas? What's the volume of gas required to keep that thing, pressurized and livable as well? You got to think about seepage through the permeation of the walls. Does it permeate? Do you need to coat the walls with some sort of substrate that would keep it from leaking out? These are things that need to be. These are technical issues that people sometimes don't really think about when you see pictures like this. So to develop this particular site, we call it LEAP-2, Lunar Ecosystem Architectural Prototype. There's a number of stages you have to go through. First, you have to understand where you're going and what's there. And this is a remote sensing stage, where we're doing surveys and what's potentially there for a location. Is there a reason to go there other than living in the tube? Is there an ore field there for mining, for oxygen or other kind of minerals? The helium-3, for example, that gives a purpose for the economy you want to develop. The next stage will be then the reconnaissance stage, where you send a robot there to go explore the cave, and you got to get down in there in some manner with the robot. to get in there and understand that if it's safe. It's essentially these skylights is the part of the lava tube that has collapsed, and that gives you the access to the lava tube. Well, if it's collapsed in one place, you want to make sure it's not going to collapse somewhere else if you're going to use that for a location to build out. So you want to do site surveys with robots you would send. The third stage then would be sending robots and humans there to camp out, to go on ground truth with the robots found, and again the inspection of the location to explore it to see what's there with humans, and then the fourth stage, maybe they've decided, okay, this is a livable location. Excuse me. Your mission is the camp out mission is probably a 3-day mission, 3 to 7 day mission. Then you got to bring down another more permanent type of habitat. Say maybe you're living there a month at a time. The more consumables you have to bring with you. Your surface operations is a little bit more developed on top. And then you get down to the stage where you start developing the complete infrastructure. And on the surface you have the full blown surface operations of landing pads and power systems, and you got a better way to get down into the pit, and you start developing the infrastructure for it inside the pit, clearing it out, and then finally at the end of the century you're developing that you got it covered up. These are kind of notional timelines here, end of the century type things. So here's a mission we have called Lido mission. This is the one we're developing to do that first reconnaissance phase operation, where we're going to send a robot there to explore it. And there are many ways to go down in there. There are a lot of companies, especially in Europe, actually, where they have got different concepts for getting the robots down, or some sort of a way to get down in there and explore the cave. I don't know if that's movie is in this one or not. Let's see if it is. Here. No, I guess that's the movie here. I'll have to bring that up later. All right, so we've been developing. I am working with. It was mentioned earlier that we have the STEM Education Foundation called Wix Foundation. We're developing a STEM education where it's called LCATs. We take students into caves and they learn about exploring, and they build field instruments like lidars or temperature sensors. And they're middle school to high school students, and we take them into caves and they learn how to be scientists in the cave and do field measurements. We're trying to develop a way to develop this robot that we're developing for the Lido mission. There's that. I'm just showing pictures here. This is kind of an older presentation, so I apologize for that. There's duplication here. Yeah. I'm sorry. I guess I thought I had a movie here I wanted to show, but it's not here. This one here is this habitat, for example. How do you get down in there? How do you deploy? How does it expand? What kind of force system? Outfit in these habitats. You have an inflatable habitat, but how do you outfit it? How do you put the secondary structures in there, like the force system and the crew quarters and the laboratories? Those are all going to be brought down separately, or are they somehow contained in this inflatable habitat? Those are architectural considerations that when you start thinking about the engineering aspects of it. Here we're just trying to show a concept for an inflatable structure. We're laying down a floor inside this habitat. Where it's brought into the two end cones or packaged, and then it expands out with these truss systems, and then the floor gets laid down. I talked about the porosity, regular porosity. How do you make sure that what's the structure for the dome to work at? So that if you're going to fill it with gas, how do you make sure it doesn't escape? And is the porosity of the regolith? We've been doing tests with that to understand how leaky is the regolith in this kind of situation. Yeah, I'm sorry. I apologize for that. I thought I had a better presentation to show you on that. Let me see if I can find something here that maybe could help with that. Give me 1 second. I'm sharing for a second. I'm going to look for something.
Thank you, Sam. We have an immediate question from Luca.
Okay, go ahead. Go ahead.
It's not immediate, but thank you. So considering the project, so how would the volume of the lava tube be pressurized to 1 atmosphere to ensure a soot-free environment? And also additionally, another question is how would an adequate atmosphere composition be provided? So considering noble gases such as argon, neon, krypton, or nitrogen in general would be very important.
Yeah, those are great questions. You know, how much, you know, just that pit itself is almost 83,000 cubic meters. That's a lot of gas. That's huge.
Yeah.
And where's that coming from? So those are very practical considerations we have to think about when we start talking about pressurizing these lava tubes. And maybe it's not the complete. That's just the pit itself. But then maybe you want to contain some sections of it in the tube. So maybe it's portions of it or just vaults or somewhere that are pressurized. But even that is still huge amounts of gas. And where's it coming from? That's my big question. If you recall the picture on that I showed about the vision on the top, there was a mining operation where they were scraping the topsoil. So there's oxygen in the soil. So maybe that whole operation is just to take the oxygen out of the soil and use that as a source for the regular.
Yeah, I mean also the helium, for example, could be used as an insulation gas because it's good in insulation in general.
Yes, exactly. Very, very much so. Okay. Let's see if I can find this thing for you. Okay, here we go. Another question?
I have a question before I give Stefan. I have a question, Sam, because you have been active as a space architect for the last 30 years, right?
Yes.
And you have also experienced teaching and you've seen students and you have been involved in real projects. I have a question concerning education. Do you see a benefit in including space architecture in regular architecture and engineering curricula, and what would that be? Or how would you do it?
Yeah, well, the answer is yes, of course. The thing about space architects and architects in general that they bring to the engineering community is they have a systems approach, an end-to-end systems approach. Architects understand the big picture, you know, the vision part of it. And a lot of times engineers, you know, they're taught to design to the interface. Just they're part of the project, they're part of the system. To the interface that they, you know, and the next part of that, the other side of the interface is another engineer's responsibility. A systems architect or systems space architect understands the complete end-to-end architecture. So, and this is the way I've always approached our projects, especially the civil engineering project we're doing with the lunar construction. It's an end-to-end systems approach. You notice I talked about rocket delivery and cargo delivery, packaging delivery. How do you package? You know, how do you bring down this stuff and how do you stage it? Even before I even began building a habitat, okay, before even beginning all that, and even going back further to the building part, the material science piece of it. The space architect has to understand the materials he's building with. Maybe not so much for orbital architecture of space stations, but for lunar surface architecture or Mars architecture. What are you going to build with? And when you understand the material, you got to understand it down in the case of these extreme environments, down to the granular level. I mean, learned that the shape of the grain of the dust is very important. It makes you understand how it forms and solidifies, and how it densifies into a solid brick, for example. So these things are it's a comprehensive view of the project you're on, that an engineering discipline doesn't really give you. You focus on electrical engineering, you focus on mechanical engineering, but not the system parts. And that's what I think is lacking in the engineering curriculums that are developed. The system engineering is probably the closest thing they have to it, but an architect brings a lot more to that whole picture in a team environment as well. I don't know if that answered your question or not, but that's kind of where it goes.
It's a start of an even more intriguing discussion, I would say. We have a question from Stefan.
Okay.
Yes. So how would a small leak affect the tube? For example, if you have a window and you have like the ceiling, which gets rough over time, and there's a small leak, how to prevent it, and how fast do you have to act?
Yeah. So with that kind of volume, I'm talking about the small leak, you don't have I mean, certainly it's an emergency. If you can locate it quick enough, or if it's small, if there's leaks, you can have sensors all over the place to understand that. And so if you can get to where that leak is in a quick time, that'd be fine. But because it's a vacuum on the outside, that leak could be temporarily repaired, but just simply pushing something, some sort of material, some sort of a stopgap measure on where that leak is, and it would, the pressure is going to go out, right? I'm sorry, the vacuum is going to, is on the outside, not on the inside, so it's not going to implode. So that's a quick way of doing that kind of thing until you get to a more permanent solution. But you can have temporary solutions for identifying where leaks are occurring. The bigger thing to deal with, I think, is the gradual leak. I talk about permeation, regolith permeation, right? Is it going to leak through the ground and then up to the surface? I mean, how dense is that wall, right? That natural regolith wall or cave wall. And that's what I talk about when I talk about permeation. And you might have to do things like, and we actually have a proposal into NASA for understand how to spray coat the wall in case those things are not going to be, not permeable as well.
Okay, thank you very much.
Okay, here I have the picture up here of the Lido mission. This is the way we're going to the way our concept is of how we would explore this lava tube.
Before humans can inhabit the moon, EXARC and Astroport plan to deploy specially designed robots to explore the lunar cave, where astronauts will eventually live and work. The Lido-1 mission is named for the mother of Artemis and Apollo in Greek mythology. Just as Leto sought a place to give birth to her twins, so does the Lido rover seek out the location of the birthplace of our lunar settlement. This reconnaissance mission involves an autonomous rover that will investigate the selected site, called the Marias Hills Pit, where the lava tube caves are located. To respect the site during first contact missions, it's important to use exploration technologies that won't disturb the pristine site that has existed for billions of years. The rover will initially land at a distance, behind high hills or other geologic structures found in the area. But carefully choosing where we land will protect the pit from rocket exhaust and plume blast material. In this way, scientists and geologists can take uncontaminated, accurate measurements of the pit and caves. After landing, the rover then travels to the lunar pit and secures zip lines. Next, the rover will deploy its payload that will aid in relaying key data about the site. The payload is a set of twin mule robots, MULE is an acronym for Multi-Utility Legged Explorer. The mules will bring cave measurement tools, cameras, power, and communication lines. They'll explore the cave to collect important data, including measuring the entire area to create a 3D map of the lunar cave and detect if gases and water vapor are present. The LIDO-1 mission prioritizes preserving the lunar cave for the second phase, which will bring humans and another set of mule robots. The robots work together. For instance, when the first mule runs out of power, it notifies the second mule. That mule is tethered to the payload module to allow for power and data transfer. The second robot is also equipped with an arm, so it can unsnag itself if the cable gets tangled in transit. The mission objective is to do a comprehensive site survey to gain an understanding of the pit and cave characteristics. This will help determine the suitability for future habitation and the eventual creation of a lunar settlement. The hope is that the explorers and scientists will travel deeper into the cave to conduct their research and confirm the structural stability for the future permanent habitation modules. The data transfer goes back to the payload box and is relayed to scientists monitoring the mission back on Earth. When the mule robot's mission is completed, they will power down. They can be revived and repowered for use in subsequent human reconnaissance missions. Once the site surveying is complete, we'll set up a base camp on the lunar surface and construct an elevator platform to lower expandable modules down the pit and into the cave for longer stays of months at a time. Eventually, landing pads, mining operations, habitat construction, and power stations will provide the basis for a permanent lunar settlement. In many years' time, the goal is to construct a dome over the pit so that the inhabitants can get out of their spacesuits and leave the habitat modules to move about freely in breathable air.
Okay, so well, that's that. Okay. Again, these are concepts, trying to convey a vision for how things could get done. There's a lot more engineering that's going to be required, a lot more practicality in terms of how this stuff actually gets implemented.
Thank you, Sam. Thank you very much. Do we have any more questions?
Yes, sorry. I would have a question. I mean, it's connected to your project, but this semester we made a project on a Martian base, and I have like a small presentation. 5 minutes will be all right with you if I just show you the presentation. It would mean a great deal to get your opinion on it.
Well, maybe something up to Sandra.
I think it's okay, Luca, but please
Yep.
ask the question, not do a presentation.
Okay, sorry.
Thanks a lot.
Yeah.
Thanks, Sam.
Yeah. All right. So in general, my question would be, our project is based on reflecting sunlight using mirrors into the Martian base so that we have complete radiation protection. So there is no visible sky, so direct visible sky from any point. So the sunlight is reflected using mirrors into the habitat. Do you think that would be something which would work?
So it's a habitat on the surface, basically.
Yeah, it's a habitat on the surface. So I'll show it with my hands. So it's shaped like an eye, let's say, and the sunlight doesn't get directly in, but gets reflected through mirrors into the structure.
Luca, show your floor plan.
Yeah, all right.
Because it's very hard to understand. And should
Yeah.
a diagram or
Sure, I will. Just one moment. Can you see my screen?
Yes.
Okay, here. That would be like this. So yeah, like this. So the diagram on the left.
Okay. Sunsets.
Yeah.
Yeah.
So the structure simulates so sunrise and sunset. Do you think that is something which is promising, or do you see a key mistake in the general concept?
No, I mean it's there've been other concepts where they bring in directed sunlight through fiber optics, that kind of thing, fiber tubes, the same sort of thing. The only thing I would question is how are you going to regulate the intense heat, I think, that would be generated.
Yeah.
Not just light, but you also have heat to deal with. You have to regulate that. But in principle, yeah, I think it's viable. As long as you can regulate the sunlight, it's going to generate heat at the same time.
Yeah, for sure. All right, yeah, that would be my main question.
Yeah.
That's it. All right, thank you.
Sure. Okay, did we get through all the questions? I don't know. Let's see. I'm looking at the chat here.
sorry, I was muted. Sam, I think there is all the questions you have answered. I have one more question. Have you worked on early prototyping yet, or do you consider working on building mock-ups of one of your projects?
Yes, yeah, we do that. As far as habitats, we haven't done a prototype habitat. More of the other technologies, the construction robotic technologies, we've been doing prototypes for that. The one thing we're developing right now is the technology demonstration robot that will demonstrate the brick making on the moon. So we have a robot that is it's going to be our first mission to show that we can actually make a brick on the moon. This robot has the end-to-end architecture of the excavating and then the processing of the regolith, the sieving it, sorting it, and then the melting of it, and the forming of the brick and placing the brick, all on one platform. Now, if you recall in the presentation, there were a number of those processes were all separate processes with different robots. We're gonna combine all that into a subscale version. Hopefully, we'll get it on the surface by 2028, and show that we can actually scoop up dirt and sieve it through a sieving system, and put it into our melter, and shape the brick and make a brick on the moon. Not make the pad, but just make a brick, and to show we can make a brick in the vacuum environment. So that would be that's beyond prototyping. That's actually a demonstration mission. But we're doing, before we get that, we're doing different prototypes of the melter and the sieving system as well.
That is lovely. And will you do the demonstration in one-to-one size?
Yes, it'll be a one-to-one. I think maybe I might even have it showed it here. I don't know if I might have passed over it. Let me see if I have it. Maybe the other demonstration. Yeah, no, it's not on this one. If you want to see it, let me try and pull it up. Am I sharing the screen? I don't know if I'm.
Not yet.
Uh, Okay, let me get the screen up here. So this picture here. So you see here in this is kind of our timeline. We're making the bricks here. This picture here is the ground version of the robot. We've got we got it to the point where we got the excavator moving, and then we're developing the sieve system. This is the ground unit that we're developing, and then we go into a flight unit. And I probably shouldn't show this picture here because we're on YouTube. Let me stop sharing. Sorry, that was from our pitch deck. Anyway, that was kind of a quick big picture of the robot we're developing.
Sorry, I'm muted again. Wonderful. So again, thank you very much. And I'm looking forward to the outcome of your prototyping, and we will see how the first structure on the moon looks like, right? With this brick
we
tiles.
got our moon yard finished, fixed, built this year, this coming year, 2026. We'll start seeing the demonstrations of these robots.
Fantastic.
In the moon yard. Well.
Okay, I thank you very much for taking the time, getting up early for us, sharing your know-how and your experience, and also answering the questions from our students. Thanks a lot, Sam.
Yeah, pleasure's mine. I'm glad to do it. And thanks for all the questions. Appreciate it very much. Good luck to you all in your future careers. And Ad Astra.
Ad Astra, let's go to the moon.
All right. Luna. Thank you. I'm going to sign off now.
Bye. Thank you.
Thank you. Bye.
Thank you. Bye.
Thank you. Bye.